Welcome back everyone. In this lecture I am going to talk about Mackey's irreducibility criterion. So, let us first see what is the motivation behind this criterion. So, if we start with irreducible character of H, so there is no guarantee that the induction of that irreducible character that is going to be again irreducible character of G. So, this is the first observation. If chi is, let us say, an irreducible character of H, so then the induction from H to G of chi, so need not be irreducible character of G. So, one can actually give very simple example of this observation. For example, one can start with the trivial character of the trivial subgroup of G. Okay, we can take H to be just a trivial group sitting inside G, and then take chi 1 to be the trivial character of this group. So, then it is not very difficult to see the induction of this trivial character of this trivial group to entire G. So, that is going to give us actually a regular representation of G. So, I will leave it as exercise that the induction of this trivial character from trivial group to G is exactly chi regular of G. So, this is the regular representation. So, we already know that the regular representation is highly completely reducible because it contains all possible irreducibles there. So, this need not be irreducible. So, then one can ask the question like when this induction is going to be irreducible if we begin with the induction of the irreducible character. So, the induction actually well behaved with respect to direct sum. So, if you start with some character which is already reducible, so then it is not difficult to see the induction of that is going to be again reducible. So, that is why we can start with chi being irreducible. So, here is the question. So, Mackey's irreducibility criterion actually gives complete answer to this question. The question is, so when the induction of any character from H to G is irreducible. Okay. So, if you think about it, we had this criterion to check some given character is irreducible or not. So, let me recall that. So, this is the fact which we proved long time back. Suppose if you have a character xi, so character means it is a character of some representation. If you start with the character xi and xi is irreducible if and only if we proved that the inner product between xi and xi must be 1. So, this is one way to check whether xi is irreducible or not. So, this actually kind of helps us to check when this induction is indeed has this property, the inner product being 1. But since induction is related to the restriction, so we need to really analyze the following. So, if you take the inner product between the induction G to H chi and then the induction H to G chi. So, if you look at this inner product, so then by using Frobenius reciprocity, so this is going to be exactly equal to chi comma the restriction applied on the induction of this chi. Okay. So, this is just Frobenius reciprocity. So, that means if you want to get a answer to this inner product induction comma induction that is being 1, then we have to see when this inner product is actually going to be 1. So, now we are going to talk about like restriction applied on the induction. So, maybe one can actually do it in much more generality instead of just restricting to only the same group. So, what we are going to do? We are going to take 2 subgroups of G and then work with that. So, before that let me just define what we call as disjoint representations, because that terminology will be used in the criterion. So, we call 2 representations are disjoint if they have no common irreducible constituents. So, here is the definition of what is called disjoint representations. So, you start with 2 representation, let us say phi and rho. So, these are representations of G and they are called disjoint representations if they have no common irreducible constituents. Okay. So, now the definition actually immediately gives characterization for the disjoint representations. So, I will leave it as exercise, and it is easy to prove that phi and rho representations of G are disjoint because they do not have any common irreducible factors. So, that means if and only if when you take the character of those representations, so they are supposed to be orthogonal, because there is no common irreducible factor that appearing in both phi and rho. So, and using the orthogonality of the characters, you can see that this inner product must be indeed 0. Okay. So, like I said, so this term uses both restriction and induction. So, because of that, what we will do, we will actually replace this H by 2 groups H and K, and then we actually try to see what happens to the in that situation. Okay. So, for that we need to actually talk about double cosets. So, I hope you are all familiar with double cosets. So, let us actually define what they are. So, instead of fixing 1 subgroups, now we are going to fix 2 subgroups of G. So, basically we want to understand what happens to this restriction from G to H applied on the induction from K to G of F. So, this is what we want to understand. So, for that we need to understand what happens to the double cosets and so on. So, note that given this H and K, we have the natural group action H cross K acting on G. So, how this H cross K acts on G? So, basically you take any elements G in G and H in H and K in K. So, then what you do, you just the H K acts on G as multiplying left by H and then right by K. So, this is the action that we are talking about. So, now what will be the orbit of this G under this action H cross K? Then we have to collect all possible images of G under this H cross K action. So, then it is meaningful to denote that orbit as HGK. So, what is HGK? You collect all the possible images HGK, where H in H and K in K. Since this is indeed group action, so you can divide G into these orbits, and these orbits are called double cosets. So, these orbits are called double cosets of H and K inside G. And we can also talk about the representatives of these double cosets, and we are indeed looking for some nice double coset representatives. Okay, so things are actually somewhat simpler if you have this H to be normal inside your group. So, the double coset representatives or the double cosets, they are indeed denoted as follows. So, we use this notation H slash G slash K to denote the set of double cosets of H and K in G. So, now I will leave it as exercise. This is a simple exercise. So, if you assume that H is normal in G, so then this the set of double cosets, they actually becomes just cosets of H. So, this H G K, so which is the set of double cosets, this is exactly equal to G modulo H when H is normal inside G. Okay, this is just follows from the definition. So, I am going to just leave it to you to check. So, now let us look at Mackey's first theorem. So, that actually kind of tells you how to rewrite this character or this function. Okay. So, let us actually state it properly. So, here is the theorem. So, this is due to Mackey. So, as before, we are going to take two subgroups H K of G. So, now what we will do, we will also set this capital S to be a complete set of double coset representatives for this the set of double cosets. So, this is the set of complete representatives for this set of double cosets, which we denoted by this. So, then what we have, so you start with any class functions on this K. So, then we can actually compute explicitly how this restriction applied on induction decompose. So, you can see that the restriction of G to H applied on induction of K to G applied on F, this is going to decompose as summation S in capital S, where now you have again induction from H intersection S k S inverse to H, and then you apply that on the restriction, where restriction is taken from S k S inverse to this H intersection S k S inverse, and then you apply F on that. So, here we need to be little careful. So, instead of F we take F power S. What is this F power S? F power S is just a translation of F by this conjugation S inverse X S. So, where this F S is again a class function, which is a class function on this S k S inverse, that is given by the formula that F s of x, like I said, it is just act exactly as F via this conjugation. Okay. So, this is the result of Mackey. So, this is actually kind of some technical thing that is needed to understand the induction of any irreducible character. So, let us try to prove this. Indeed, the proof actually uses some important construction of the correct set of left causative representatives of K in G. So, let us see like how to get that. So, we have fixed already the double coset representatives of H and K in G. So, we are going to use this capital S to get left coset representatives of K in G. So, that is the ultimate goal. So, how do we get that? So, what we do for each S in capital S, so we are going to fix first of all left coset representatives of H intersection S k S inverse in H. So, for each S in capital S, let us call this V s. So, this is a complete set of representatives of the left cosets of H intersection S k S inverse in capital H. So, in particularly note that V s is subset of H. Okay. So, once we have this then it is easy to see that you can write capital H as disjoint union of V in V s, where V times this left coset you take H intersection S k S inverse. So, this is what we get, and this union is disjoint union, that is why I am using dot here. So, this union is disjoint union. So, now what we can do? So, we can use these representatives to rewrite H s k. So, H s k is the double coset. So, if you just take this H s k, you can see that this can be rewritten as follows, which is exactly H s k S inverse S. So, if you just look at this term, this H can be written like this. So, you can see that this is exactly given by the union of V in V s, V H intersection S k S inverse. So, where S is fixed actually, times S k S inverse, and you get S. Now, note that, so this is going to be a subgroup of this, okay, H intersection S k S inverse is a subgroup of S k S inverse, and that would imply that the product H intersection S k S inverse times S k S inverse is going to be exactly equal to S k S inverse. So, now using this we can simplify H S k as union V in V s, and then so this just gets merged as S k S inverse. So, if you replace this by S k S inverse, then this exactly equal to V times S k S inverse S. This S inverse S will get cancelled. So, what you get is exactly V S k. So, this is what we get it as union, and we can prove that this union is also disjoint union. So, moreover we get that this union is disjoint. Indeed, how one can check that? So, let us say we have actually some intersection. So, since all of them are left cosets of K, if there is an intersection they should be equal. So, let us say V s k is same as V dash s k. So, then in that case V inverse S inverse V dash S is going to be element of K. So, where this V dash comes from, let us say V s. Okay. So, now we have this sorry, we should rewrite this. So, I want to multiply so V dash S and then V inverse S inverse. So, this is going to be element of capital K. So, that means V inverse V dash, that is going to be element of SK S inverse. Now, note that already capital Vs is subset of H. So, this product is going to be element of H. So, this is going to be in the intersection. If it is in the intersection, then you can see that this is going to give us same left coset representative of this subgroup. So, VH intersection SK S inverse is going to be equal to V dash SK S inverse intersection H, but that is not going to happen because we have chosen Vs as a complete coset representatives of this left cosets of H intersection SK S inverse inside capital H. So, that tells you that this will not happen. So, that this means this will not happen. So, that means this is indeed disjoint union. So, this is something we have now, or otherwise from this we can conclude V equal to V dash. Okay. So, now we can see that we have this T s for each S, where which is V s S in capital V s. So, for each S in S we have this T s. So, now we can collect all of them and then make this capital T. So, this capital T is just the union of T s S in capital S. Now, note that this capital T is going to be the set of coset representatives for the left cosets of K in G. So, that is what we are going to prove. So, first we are going to prove that this capital T is indeed disjoint union of this T s. So, this is also disjoint union. So, let us check that quickly. If it is not disjoint, then what will happen? We will have V s equal to V dash S dash for some V dash inside capital, sorry, V will come from, V comes from V s and V dash will come from V s dash. So, now from this we can easily see that H V S K is going to be equal to H V dash S dash K, and that would tell you that because V dash both are, these both are elements of H. So, that would imply that this is equal to H S K equal to H S dash K, and since S and S dash they are again coset representatives for these double cosets. So, that would imply that S equal to S dash, but since S equal to S dash and this equation V s equal to V dash S dash will imply that V equal to V dash. So, this proves that this union is indeed disjoint union. So, now we are going to claim that this T is a complete set of representatives for the left cosets of K in G. So, the claim is T is a complete set of representatives for the left cosets of K in G. So, this is what we want to claim. So, let us actually try to verify that. So, note that G is nothing but union of H S K S in S. So, this is the disjoint union. So, now if we use this fact H S K, we wrote it as, which is equal to union of V S K, where V comes from V s. So, this is something we already verified. So, then this is going to be equal to disjoint union of S in S and then disjoint union of V in V s. So, then it becomes V S K. Now, since T s is nothing but V s V in V s, so you can see that this is exactly equal to the union of T T k, T in capital T. So, now you can see that all these are disjoint union. So, what you get at the end is also disjoint union. So, that proves that capital T is a complete set of representatives for the left cosets of K in G. So, now this indeed helps us to do the computation. So, let us compute the induction from K to G of f of h. So, we have fixed this f, which is an element from the class function on this K. So, this is fixed. Now, let us compute this induction from K to G of f of h for h in h. So, then what we get? We get exactly this is equal to summation T in T, because capital T is the complete set of representatives. So, this summation T in T f dot T inverse h t. So, that is what we get. So, now this is exactly equal to summation S in S and then V in V s. So, because we are rewriting this capital T as union of T s and T s we know what it is. So, if you rewrite that, we get this is exactly summation over S in S and summation over V in V s, such that f dot of S inverse V inverse H V s, where note that T is V s. So, T inverse is S inverse V inverse. So, this is the substitution that we are doing. So, now if you just look at this function, so basically I can replace this by this f s. So, recall f s of x is defined to be f of S inverse x s. So, if we use this notation, then we can replace this as follows: the induction of from K to G of f applied on h. So, this is what we want to compute. So, that is exactly equal to the summation. So, now I am replacing this dot by f s. So, you get summation S in S, again another summation where V runs over V s. So, now the f dot we want to replace by f. So, that means the term that we have it here V inverse H V. Okay. So, recall f s of x is f of S inverse x s. Okay. That is what we want to replace. We want to replace f dot to f. So, then you can see that these terms that are there, that should be inside your capital K. So, the terms that that will be there is these terms. Okay. So, that should be in capital K. So, what is the meaning of that? S inverse V inverse H V s is supposed to be in capital K, which is if and only if V inverse H V should be inside S K S inverse. So, that is how we get this S K S inverse, and we can substitute that there here. So, we take this V inverse H V comes from S K S inverse. So, now if you apply the restriction on this, so the restriction of so now we want to take the restriction of this H G to H, apply it on this induction K to G on F. So, this is what we want to compute. So, this is applied on H, this is what we want to compute. Then this restriction is going to go inside this summation. So, this is going to be summation S in S, summation V in V s, again this term V inverse H V is going to be an element of S K S inverse. But now we want to do the restriction to H. So, this going to be restricted to intersection with H. Similarly, here this F s you want to restrict it to H. So, then that is going to be exactly equal to the restriction of S k S inverse to H intersection S k S inverse applied on F s of V inverse H v. So, when you do the restriction to H, so this is indeed a function, F s is a function on S k S inverse. So, that is something you want to restrict to H. So, that means you will be only able to restrict to H intersection S k S inverse. So, that is what you get here. So, now if you put them together, you can see that this part is indeed given by the induction. So, if you simplify using the induction, you can see that the left hand side which we wanted to compute, the restriction of G to H, the induction K to G of F applied on H is exactly going to be equal to summation S in S. So, like I said, this entire term in this red box. So, this is indeed given by the induction. So, where the induction happening from H intersection S k S inverse to H. So, this is exactly given by the induction of H intersection S k S inverse to H, and then you apply that on the restriction S k S inverse restricted to H intersection S k S inverse applied on F s. So, this is what we are getting. So, we do not need to evaluate at H. So, this is what we get it at the end. And this is what we wanted to prove, and yeah, we completed the proof. And we will see that how to use this equality in order to get the Mackey's irreducibility criterion maybe in the next class. So, I will stop here.